Hello everyone, myself Ankita, Faculty of Department of IT, Akgec. Today I am going to discuss second topic, that is uninformed search for Unit 2 of course KCS 071 of AI. Now, in the last video I have discussed about how we are trying to solve problems from AI. In such a scenario, we have to formulate the problem as search problems. Now our task is to find the goal state in such problems, and the process of finding that goal will depend on the type of search technique that we have used. So one of those search techniques is your uninformed search. In uninformed search, before starting this, we have to be clear that we have a search space in which we are at a starting node, and we have to search for the goal node, and we have to search for a path to the goal node. So in uninformed search, we only know the algorithm, and we try to explore the search space in some predetermined manner. Okay, so we don't have any specific information or any heuristics or any domain information of the problem. So basically we don't have any information of the problem, and we are just trying to visit the node so that we reach the goal node, right? So advantage is that it is simple. Obviously it's simple. It's inefficient because as our search space increases, the problem's complexity also increases. Example is, these are the algorithms that we are going to cover, that is BFS, DFS, uniform curve search, iterative deepening search, and bidirectional search. BFS or breadth first search algorithm. It is an uninformed search strategy, as we are studying the different types of uninformed search strategies. So the first strategy in your uninformed search is your breadth first search. Now breadth first, before starting the breadth first search, we have to know that we are at a starting node and we are searching for the goal node. And there is two terminologies that we have to keep in mind. That first is your visiting the node, that we have known that node exists, and second is your exploring the nodes, when we are expanding the node to find out their successors. So in your BFS, we search the tree breadth wise, and it means that we start searching from the root node and expand all the successor node at the current level. So the nodes which are present at the current level, we are exploring all those nodes before proceeding for the next level. It is implemented through your FIFO queue. Now FIFO queue means that first in, first out. It means those nodes which has been visited first will be explored first. So this is the algorithm. Algorithm state, we start with the initial state as the root node, and then we will enqueue the root node into the queue. So while the queue is not empty, we will dequeue the node from the front of the queue, and then we will explore the node and enqueue its unvisited neighboring nodes. So then we will mark the dequeued node as visited. Then we will repeat the process till we find the goal state or our queue is empty. Now this is an example. So suppose we start with your S node. This is your starting node, and this is your K node is your goal node. So what we'll do, we'll make a queue. First of all, we'll make a queue, and at this beginning, we will add S to the queue. Now there's only one node in the queue. We will dequeue it, and then we'll try to know what is the successors. The successors are A and B. So we'll put them in the queue. Okay. Then again, there are no successors, and it is not a goal node, so we'll proceed further. Then again we'll choose A, and then we will dequeue this node and we'll add this node in the list, and we will put their successor node in the queue. Okay. Again, after exploring A, we have visited all those nodes, but we won't explore these nodes. We will explore the next node in the queue, that is your B. So we will try to explore B and add their successor in the queue, that is G and H. So this process will continue till and at each step we will check. Before exploring the node, we will check whether that node is a goal node or not. So you can see we are exploring in this fashion. That is, we are exploring the nodes at this current level, and then after exploring all the nodes at a level, we are moving to the next level. So this is the final path to the goal, right? So this is your breadth first search. Now, advantage is that it provides you a solution if there is a solution exists. So, if there is a solution, it will give you the most optimal path to the goal. Disadvantage is that it's very inefficient in large search spaces. These algorithm takes exponential time to find out the goal node. Next is your evaluating efficiency of your BFS. Now, BFS is complete because it guarantees you to find you the solution. Optimal, it gives you the best path to the goal node. Time complexity is order of b to the power d, where b is the branching factor and the d is the depth at which we have explored the tree. Okay, it is not the total depth of the tree, it is the depth to which we have explored the tree. Whereas the same complexity is, space complexity is same as order of b to the power d. Your next algorithm is your uniform cost search algorithm. Now, uniform cost search algorithm is similar to your BFS, but in BFS we have unweighted graph, whereas in UCS we have weighted graph. Okay, so it is just the concept is same, but we have to keep in mind that now their weights are attached to the path. Also, we are aiming to find the least cost path to the goal. So now we have the path, so we are aiming to find the least cost path to the goal. That is your lowest cumulative cost to the goal node. Now, uniform cost search algorithm is implemented by a queue, but here we have the queue as your priority queue. With the path with the lowest path cost will have the highest priority. Now, this is the algorithm, same. This process of it is same as that of BFS, but here we are using the priority queue. Otherwise, it is same as that of BFS. Now, here we can see again we will make a queue. Okay. Now, this is, remember, this is a priority queue. So, S is there, and then we will check what are their successor. We will explore S. So, there is A and B. Now, the path for A is 1, whereas B is 4. Okay. So, which node we will select for exploration from these two? A. Why? Because the cost of this node is less. So, we will explore A. Okay. So, we have explored A. And then from A, there are two paths, C and D. We have explored here C and D. C's path is 4. 3 plus 1, 4. And D is 1 plus 2, 3. Okay. So, again, the path through D is less. So, we will DQ this and we will follow this. Now, again, we'll explore this. There two are F and G. F and G. For F, the path cost is 6 to 7. And for G, it is 5 and plus 6. So, what we'll do? We will move to G, where G is our goal node. So, remember, at each step before exploring, we will check whether my node is goal node or not. At the end, when we found that's a goal node, we will stop our search and return the path. Now, the path here is S to A to D to G. So, this is your final path. Okay. Now, advantage is that is optimal, because since it is based on your BFS, BFS is optimal. Therefore, you can say UCS is also optimal, and it does not care about the number of steps involved in searching and only concerned about the path cost. This is your disadvantage. Okay. So, in such cases, the algorithm can stuck in the infinite loop. Next is your evaluating efficiency of UCS. It is a complete algorithm. It is optimal because all these points are same as that of your BFS, because it is just an extension of BFS. Okay. The space complexity is order of b to the power d, and time complexity is order of b to the power 1 plus c star upon epsilon. It is similar. Why? The minimum optimal cost is c star and the lowest cost is your E. Okay. Next is your depth first search. Now, depth first search is an uninformed search strategy that explore as far as possible along the each path from before backtracking. So, what happens? It explores through a branch entirely, okay, before backtracking. So, it will select a path and it will explore till it is end of that path, okay. And if it's find a goal node is good, otherwise it will backtrack. So, since it is backtracking, you can say it is a recursive algorithm. It will traverse the tree or a graph structure by following your recursive algorithm. So, it uses the data structure as your stack. Why? Because here we are not exploring breadth wise, we are exploring depth wise. So, we have to use stack. The algorithm is same as that of your BFS, but here we are using a stack, and the most recent
node will be explored first. In your BFS, the first node that we explored will be first node that we have visited first will be explored first. But here in DFS, the last node that we have visited will be explored first. So example is this. Suppose we'll start with your S node. We will make use of a data structure called stack. Then what we'll do? S. Then we will add the successor of these nodes. So suppose we have added H and then we have added A. Okay. So this is not a goal node. Then we will move to the other node. So we will pop A. We will pop A, and then again we will add the successors of A to the stack. So here successors are B and C. So we added B and C. Okay. Now again, A is not a goal node. So what we will do? We will pop B and explore B. B exploration after be found D and E. So here it will be D and E. So we will move like this. After D, there are no further child nodes of D. So what we will do? And we still haven't find the goal node, right? So the two condition is that either tree ends at that branch or we find the goal node. So nothing has happened. So what we'll do? Backtrack. We will backtrack by following this path and we'll reach G node. So this is your path to the goal. Okay. So this was your DFS algorithm. Advantage is that it will require less memory as it only needs to store the stack of the nodes and the path. It takes less time to reach the goal if it traverses in the right direction. Disadvantage is that there is a possibility that many states keep reoccurring. There is a guarantee of finding the solution. There is no guarantee of finding the solution. Now I will try to explain this disadvantage in the form of a diagram. Suppose this is your goal node. Okay. This is your starting node. Sorry, this is the starting node, and we have these two branchings are starting from this node, and here there are infinite number of nodes in this branch. Suppose we have started our search using DFS and we start to explore this node. Then according to DFS, which node will we explore first? This node. So if the goal node is suppose this. So if we are following a DFS approach, what we can do? We can stuck in this infinite loop indefinitely. We will never be able to find out the goal node. Okay. So this is the major disadvantage, is that it goes deep down searching and sometimes it may goes to the infinite loop. So here, if the goal node is over here and this branch is having infinite number of nodes, we will stuck in this loop indefinitely if we are following your DFS algorithm. Next, if evaluating efficiency of DFS, is DFS complete? No, it is not a complete, because it can get stuck in some places. So it won't give you solution in such cases. Optimal, it is not optimal. When it's not complete, how can say it is optimal? Next is time complexity. Now time complexity is order of b to the power m, where m is the height of the tree. M is the maximum depth of the search tree, or because the height of the tree. So d, that is your m. Whereas the space complexity is order of b into m, because here we are only keeping one node in the stack, not entire frontier as that of your BFS. Next is your depth limited search algorithm. Now, depth first search limited search algorithm try to resolve the problem of infinite loop in your DFS. So in this, we are trying that it is extension of DFS where it is depth first search with a predetermined limit. So we are fixing the depth of the tree beforehand, and we are just exploring the nodes till we are just exploring the node till that depth only. So depth limited search can be terminated with two conditions failure. First, if there is no solution, that is standard failure value, and other is cutoff failure value when the depth increase, when it defines no solution for the problem in a given depth limit. So we have defined a depth limit, and if the goal node is beyond that depth limit, it won't be able to find the solution and the program will end. Now suppose here the depth limit is d is equal to 2. So here d is equal to 2. So it will assume that t and this algorithm will assume that that your tree end at this location. Okay. So it will start searching. If the goal node is j, so what will happen? It will search in depth first search. It will not now at this moment, it will assume that C does not have any successor nodes. And what it will do? It will just start at backtracking. And when it backtracks, it will reach the goal node at J. Okay. But suppose your goal node is H. If your goal node is H, then using your depth limited search, you won't be able to find the path to that goal node H. Why? Because your depth has been limited to this level. You won't, the algorithm won't search beyond this level. So it is the disadvantage of your depth limited search. Advantage is that it is memory efficient, and disadvantage is that it can be terminated without finding the solution. So if your goal node is not at the depth which has been fixed beforehand, then you won't be able to find the goal node. Efficiency of it is complete, it is not complete, it is not optimal, and it is a special case of DFS. It will not optimal even if L is less than D. Time complexity is same as that of your DFS, and space complexity is also same as that of your DFS. Next is your iterative deepening depth first search. Now this is also an improvement to your depth limited search. In depth limited search, we have your depth defined right beforehand only, but now what we are doing, we are gradually increasing the limit until a goal is found. So in your iterative deepening depth first search, we are gradually increasing the limit until a goal is found. So this algorithms search up to a certain depth limit, and it keep increasing the depth limit after each iteration. So for each iteration, it will increase the depth limit by 1 if it does not found any goal node. So search algorithm combines the benefits of your BFS and DFS. Now example, this is your example. Okay. So in first iteration, suppose this is a goal node and this is your starting node. In first iteration, I will consider depth to be 0. In first iteration, I will consider the depth of tree to be 0. So what I will do, I will search and I will check whether my A node is goal node or not. It is not a goal node. So what I will do, I will increase my depth limit. That is D is equal to 1. So at D is equal to 1, I will explore A, B and C. Okay. Again, I haven't found my goal node. So what I will do, I will increase my depth limit to 2. Again, I will start from here. Okay. I will again start from A. I will visit B. I will visit D. I will visit E. I will visit C, I will visit F, and I will visit G. So in this fashion, I can find out the goal node in your third iteration. Okay. So I can change the color to show you. So what will be a third iteration? I will visit this node, then this node, this node, this node, this node, and this node. This will be our path in your iteration number third. So in third iteration, I will be able to find out my goal node. And if the goal node is suppose K, so if it is K, so it will take 4 iterations to find out the goal node. Advantage is that it combines the benefits of your BFS and DFS algorithm, and in terms of fast search and memory efficiency. The main drawback is that we have to repeat all the work in the previous pieces. So we have seen that we have explored A 3 times in the 3 iterations. So I am repeating my search again and again. Because every time I am starting my search from the starting node. So we can say here that we have to repeat all of our previous work again. Evaluating efficiency of your iterative deepening search complete. This algorithm is complete if the branching factor has a finite time. It is optimal if the path cost is the non-decreasing function of the depth of the node. Complexity is same as that of your DFS, that is order of B to the power D, whereas space complexity is of B into D. Next is your bidirectional search. Now, bidirectional search, you can think of in a scenario that you are residing at a location A and your friend is residing at location B. Now, you have to meet. So, what you can do, you can choose a location C, and in that location, both of you can come from your respective location and meet at C, right? The same concept is used in your bidirectional search. So, here, this search algorithms perform 2 simultaneously searches, one forward from the initial state and one backward from the goal state. So we have an initial state, we will having a goal state, and we have to find out the path from this to this. So we will perform two searches. One is your forward search from forward to backward and other from backward to forward. So in the midway we will meet and this whole will form the path from the start node to the goal node. Okay. So bidirectional search can use search techniques. So we can use any search techniques from these two algorithms. We can use BFS, DFS, UCS, DLS, anything. Now what is the motivation? Motivation is that if my time complexity for search algorithm is order of B to the power D, okay. But if I am having my search space, so now my complexity will reduce to half. Order of B to the power D by 2 for this and order of B to the power D by 2 for this. Okay. So obviously this one is way less than order of B to the power D. So this is our motivation. Okay. So this is always less than this. Therefore, we can use bidirectional search. Now in the below search tree, bidirectional search tree is applied. So here we are dividing the tree into two parts, that is first part and second part. From here we are forming the forward search and from here we are doing the backward search and we are meeting at 9. So we are dividing our whole graph into two subgraphs. Example, you can see, suppose this is my starting node and this is my goal node. So this is my starting node and this is my goal node. So I will start from searching from here and I will follow the path and till D, and again from G I will follow the path, I will meet at D. So these are your two search while performing your BFS. So I am using your BFS algorithm in both ends and the final path will be your this. So we are combining these two paths. This path has come from your G node, if we have started from G node, and this will come when we have started our search from A node. And when we are combining the result to find out the complete path from source to goal node. Now, advantage is that it's faster than traditional search by exploring the search space simultaneously. Obviously, it will be fast. And also, if the effective branching factor is reduced, okay, you have seen how. Now, bidirectional search disadvantage is that it requires storing visited node from the both directions. So, obviously, it will lead to the increased memory consumption. The bidirectional search would also know the goal state in advance. So we have to know the goal state in advance. Therefore, then only we can start our search from the goal state, right? Also, the coordination and synchronization between two searches introduce additional overhead in terms of your implementation complex. This is the disadvantage of your iterative deepening depth first search algorithm. Now, it is complete if you use BFS. It is optimal if you use BFS. Time complexity is order of B to the power D by 2, but in the worst case, the complexity will be order of B to the power D. Same as that goes for your space complexity. Now, when we try to compare, we can see the various algorithms and the comparisons, and we can find the best algorithm to work is your bidirectional search. It is complete, it is time and space efficient, and also it is optimal. Now, what's the problem of your uninformed search? First, it is doing blind exploration. It lacks domain-specific knowledge or heuristics. So they explore the search space without any information about the problem space. So what happens when we search without having any domain information? So when the search space increases, it requires extensive exploration and irrelevant and unpromising nodes. So we are searching in the entirety of the search space, and at the end we get exponential time complexity and space complexity as well. So therefore, it gives rise to other set of algorithms called as informed searches that we'll be discussing in the next video. Thank you.